Now I want to take a look at a few examples of what's known as optimization problems. And by optimization, what we mean is we're trying to either maximize or minimize some quantity. You may be, for example, building a container. You want to maximize the amount of volume inside the container. Or you might want to minimize the amount of material used to build that container. You may be trying to find the maximum area or volume that will fit in a certain space. You might be trying to minimize the distance you have to travel to get from point A to point B. There are obviously business applications where you're trying to maximize maybe profit, minimize perhaps spending. So that's what all these problems are about, is finding the max or the min of something. You will find, at least students typically find, that the hardest part of these problems is just getting them set up. Once you have an equation, taking a derivative and using, at least my preference would be to use the first derivative test. Once you get to that point, it's not so difficult, but it's just getting them set up. I would advise that whenever possible, a sketch or drawing of some sort will be helpful. Again, when possible. There are also a couple of the other little tricks or techniques that are indicative to certain problem types. So let's get started. First of all, for the first problem, it's going to deal with volume and surface area. So let's say that we had 1,200 square centimeters available to build a box. This box is going to have, its characteristics are going to be, it's going to have an open top. That's important because our material will not therefore be used in the building of the top. It is, as I said, it is a box, but this box is going to have a square base. All right, and then pure and simple, the reason for having the square base is to cut down on the number of variables we have to deal with. All right, and the objective in this particular case is to build this box in such a way as to maximize the volume. We only have a certain amount of material to use, and we want to maximize the volume while using that exact amount of material. All right, so the volume of a box, and most of these problems start off with, or at least a lot of these problems start off with something simple, like you would have seen in, perhaps, in this case, a geometry class. So we'll start off talking about volume. Volume of a box is length times width times height. All right, but in this particular case, again, as I mentioned earlier, they've said we have a square base. So this volume equation can be simplified. And if we say, well, the square base is just going to measure x, we're going to use x to represent the measurement of the base, then the volume equation becomes, instead of length times width times height, it becomes x squared times height. That becomes our volume equation. All right, so this is the equation we need to either we're going to need to maximize. But my problem is, and this is going to be a problem you have a lot, I've got too many variables in here. All right, I cannot deal with two different variables when I'm taking a derivative. I only know how to take a derivative in one variable. So we need to look back and see what other information we were given that might be helpful. Well, they told us that you only had 1,200 square centimeters of material. That means the area, the surface area to be specific, to use the right nomenclature, the surface area of the box has to be 1,200. So let's figure out what the surface area of that box would be. First of all, the bottom of the box measures x by x. So that's an x squared. That's just the bottom. There is no top, or I'd put another x squared in there for the top. All right. Now, the box has a height of h. So if you think about, sort of picture in your head, the right-hand side of the box, it's going to be a rectangle measuring h high by x. So the right side is an hx. The left side is an hx. The front will be an hx, and the back will be an hx. And I probably could have saved time by saying that since the base is square, all four of the vertical sides are the same. So the surface area of 1200 is equal to a x squared plus a 4hx. Okay, now what that brings me back to is this equation that had too many variables in it. This additional piece of information, 1200 being the surface area of the box, has allowed me to set up an equation that has an h in it right here, as well as the x's. All right, so what I would do is I'd move the x squared to the other side, divide by 4x, and that gives me my h. All right, and I could then take that h, now that I know what h is, and put it back into my volume equation. Because again, my goal was to get the volume equation down to only one variable. So volume, which has just become a function of x and x only, because I'm removing the h, is equal to x squared times what I just found for h, which was the 1200 minus x squared over 4x. All right, I will multiply this out and do some other simplification. For example, this x will cancel one of those. The 4 on the bottom can come out front. And then, oops, it's not a function of 4, it's a function of x. And then I will distribute the x through, leaving the 1/4 out front because there's really no dire need to distribute that. All right, so now what I've got is a function that gives me the volume of the box for any particular x value. All right, so what I would do is take a derivative of that. And what I will get is of course, when you take a derivative, constants that sit out front just remain out front. That's what I get. All right, I will take my derivative. Set equal to 0 because I'm going to look for critical numbers. The 1/4 is irrelevant here. Divide by 3 on both sides here. And use extraction of roots. Now, technically, extraction of roots says you get 2 answers. Technically, I get, oops, 220, a positive and negative 20. But remember what your x represents. The x represents the physical volume of a box. So the negative is an impossibility. X equal 20 is my only critical number. All right, 20 is the only critical number that's actually useful, the only one that makes any sense whatsoever. Okay, it makes no sense for anything else, for that to be anything else but a 20. All right, and since I've only got one critical number here, it has to be my extreme value. There really is no other option. But if you want to be 110% sure, I can set up a number line for the F primes, mark it at 20, and I can do some testing. All right, okay. And I'm gonna let the calculator help me out just a little bit. If I put in the 1/4 times 1200 minus 3x squared, I put that into the calculator and set up a table. Clear out all the old numbers here. Keep hitting the graph button. Table. All right. And get rid of some of the old numbers. Pick a number lower than 20, like maybe a 10. Pick a number higher than 20, like maybe a 15. And higher than 20, like a 25, I should have said. You notice that the function, the derivative went from saying that it's an increasing function to a decreasing function. The function went from increasing to decreasing around 20. So 20 is a max. So therefore, the box should measure 20 by 20 by, now we need to figure that last dimension. This is just the base of the box. Now we need to figure its height. Figure its height, you use the equation that I found that tells you what height is in terms of x. So I would go 1200 minus 20 squared, which is 800, divided by an 80, because that's 4 times 20, and it's a 10. So if you want to make a box with an open top and a square base using 1200 square centimeters of material, you'll make it a 20 by 20 by 10 box. That is the box that holds the absolute maximum possible volume. All right. So again, optimization can be as simple as a problem. We're trying to maximize volume of an object. You may be trying to minimize material used. This time material was set constant and we maximize the volume. All right, let's look at another example. Look at something a little bit different. All right, let's say we want to find the points on the ellipse. The ellipse defined by 4x squared plus y squared equaling 4. Okay. We want to find the points on the ellipse that are the farthest from the point one, 0. Right? So what would that basically look like? Well, this ellipse can be rewritten, at least my preference would be to write it as x squared over 1 plus y squared over 4 equaling 1. That shows that you have an ellipse, first of all, centered at the origin. We know it's an ellipse because this is a plus and it's set equal to 1. You sort of review your conic sections. You should remember that. And that tells us that in the x direction, it goes out. Its semi-minor axis goes out a distance of 1. And on the y-axis, its semi-major goes out a distance of 2. I'm a horrible artist, but you get the idea. Okay, that's basically your ellipse. All right. And we want to find the points on the ellipse that are the furthest possible distance from 1, 0. Okay, that's what we're trying to do. All right. So what we will do is set up and make use of the distance formula. Remember, the distance formula for a couple of points on the graph says the distance from 0.1 to 0.2 is the square root of x2 minus x1 squared with y2 minus y1 squared. Now, one of the tricks with these types of problems, it's a very handy trick, is you will find that if you're trying to maximize or minimize distance, you'll get the same results if you maximize or minimize distance squared. What that does is it means you do not have to deal with this square root part. So if that's my distance formula, and my distance squared is just x2 minus x1 squared plus y2 minus y1 squared, all right? So what are we trying to find, or what distance is it we're trying to maximize? We're trying to find a maximum between the point 1, 0. So we'll call that my x1 and my y1. It'll play that role. And some other arbitrary point that's on this curve that we will just call x and y. So putting that into the distance formula, it's going to be an x minus x1, which was a 1 squared, plus a y minus a y1, which was a 0 squared. This simplifies a little bit. The x minus 1 squared, you could choose to FOIL that out, but I don't think you're really going to have to. Y minus 0 is y, and that just becomes a y squared. All right? So this is the function that we need to maximize. All right? But it's got too many variables in it. It's got an x, and it's got some y's in it too. All right? Can't have that. So we go back up here and we say, well, if you look at the ellipse in the form they originally gave it to you, this can easily be rewritten into y squared equal 4 minus 4x squared. All right, so bringing that back down here, distance squared just became a function of x, and it's an x minus 1 squared plus the y squared, which is the 4 minus 4x squared. And now seeing this written this way, I think I might just go ahead, why not, go ahead and FOIL. It's an x squared minus a 2x plus a 1 plus a 4 minus a 4x squared. So my distance squared as a function of x. Cleaning up a little bit is a negative 3x squared because I combine those two. A minus 2x and a plus 5. So when I take the distance squared function and take its derivative, I get a negative 6x minus 2. I take negative 6x minus 2, I said equal to 0. Add the 2 to the other side, divide by negative 6, and I get an x of negative 1/3. Okay, the x value of negative 1/3. Shouldn't be a surprise to you that the x value came out negative, because points on this ellipse that are furthest away from here are definitely going to be on the other side of the y-axis. All right, so the x value in question, again, is over here at negative 1/3. This x value is a negative 1/3, right? And plugging that back in to the original, 4 times negative 1/3 squared plus a y squared equals 4. That is a 4/9. If you square the negative 1/3, you get a 9 times 4. There's where the 4/9 comes from. Plus a y squared equals 4. Subtracting y squared is a 4 minus a 4/9. So subtracting that over to the other side. And so when I do that subtraction, I get a 32/9, I do believe. All right. So from that point, you just take a square root. All right. And I'm just going to choose to extract roots because it's easier. Square root of 9 is 3. Square root of 32, I'll just leave it as it is. You could take things out of that square root, but I'm beyond caring about that. All right, so the y value up here would be, and I didn't leave myself enough space, square root of 32 over 3. Now, we notice that there's symmetry to this situation. So where did the negative come from? What's the deal with that? On the previous problem, we threw out a negative because it didn't make sense. On this problem, it makes perfect sense. Because negative 1/3 and negative square root of 32 over 3 are equidistant from that point. So they both make sense for a maximum distance type answer. And so both of those answers are reasonable. Both of those are the farthest away they can possibly get from the point 1, 0. All right. Again, so the main trick with that one was to remember, use distance squared instead of distance. It's a much easier function to work with. And if you maximize or minimize distance squared, you will max or minimize distance, right? Another one that I want to look at is a problem that deals with area, all right? And at this point, since we just did that last one, I might just set this one up and leave it at that. This says, find the dimensions of the rectangle of largest area that has its base on the x-axis. So we're going to draw a picture here. We're going to have a rectangle sitting on the x-axis, and the other two vertices above the x-axis on the parabola, y equal to 8 minus x squared. All right, so the parabola 8 minus x squared would look something like this, hitting up here at 8, and the rectangle they're talking about that they want to maximize the area of, as they said, sits on the x-axis with its other two vertices on that parabola. So the rectangle they're talking about looks like this. All right, with a rectangle, the thing to remember is its area equals length times width. All right, now looking at this drawing, first of all, what's the length of this rectangle going to be? Well, if this is an arbitrary x value on this x-axis, then the length of the rectangle is 1, 2x. And the width is here. The width is the y value. But they told us that it has to touch this parabola. So the y value is 8 minus x squared. So the area just became a function of x, and it's equal to a 2x times an 8 minus x squared. So on that one, I would distribute. And it should be very straightforward to take a derivative and maximize. All right, now, physical limitations. Physical limitations. If you look at this parabola, it hits the x-axis twice. And it's going to hit at 2 squared root of 2 on the right-hand side. And it's going to hit at negative 2 squared root of 2 on the left-hand side. And it hits at 8 up top. All right. So therefore, as far as limitations of x are concerned, first of all, x needs to be greater than 0. If x equals 0, the rectangle just went flat and has no area. And our goal is to maximize the area. All right. And so we don't want it going flat and having a 0 area. Also, x needs to stay below 2 square roots of 2 because it'll go flat again if x goes out to 2 square roots of 2. All right, so just from the sketch, we can put some restrictions on x and figure out our maximum area just by doing a first derivative on this particular equation. Again, that should be very straightforward. You should be able to walk through that pretty quickly, right? Um, so let's see, there's area problems, trying to make sure I covered all the points. Distance problems, area and volume and distance problem. And so, again, you will find that the hardest part of this material is just getting these equations set up. I wanted to give you 2 or 3 examples as to how the setup should proceed. And again, from there, it's just taking a derivative and finding maximum min.